Hello everyone, welcome to the second video of the course. In this video, we will be talking about the operating principles, advantages and disadvantages of radial flux, synchronous reluctance motors. So, in the previous section, we discussed the course objectives, and here is the benchmark induction motor. The explanation of these slides is available in induction motor design course, and you can refer to those videos. Yes, and then continue this video. Anyway, so here you can see the structure of a synchronous reluctance motor. The stator core is slotted and we have a distributed winding on it, similar to induction motor. And here we have the rotor core, and in rotor core we have several flux barrier layers per pole. Yes, here we have one flux barrier layer, 2, 3, and 4. So the aim is to achieve the maximum rotor magnetic saliency ratio as much as possible. Yes, to generate a good amount of reluctance torque. So, yes, the winding is distributed similar to induction motor, and the rotor geometry is different. We considered this structure, but to generate the reluctance torque, we have several topologies. Yes, this is the switched reluctance motor, the rotor core of the SRM, and we have two synchronous reluctance motors here. The direction of the stacking here is similar to this one, and this is the transversally laminated anisotropy or TLA structure, and this is axially laminated anisotropy. So this is the ALA structure. So the difference between the switched reluctance motor and synchronous reluctance motor is the drive type. Yes, we have sinusoidal currents here, FOC control, but here we excite the phase windings sequentially to generate a continuous torque. So the operation of the drive is different, but here we have the same waveforms for current, but the difference is the direction of the stacking. Here, this structure is similar to this one, and manufacturing is similar. Yes, we have laminated core, but the manufacturing of this structure is more complicated. However, the saliency ratio that we can get from this structure is higher than this one. Yes, but from manufacturing point of view, this structure is preferable. So we will consider this structure, TLA structure, and we will design the motor and analyze the motor using the 2D finite element method, and so on. Here you can see the D and Q axis of the rotor. So we should consider a convention. Yes. And as you know, to design a synchronous motor, it's good if we transform quantities in the rotor reference frame and plot the vector diagram in the rotor reference frame. and analyze. So we should consider a reference frame and a reference direction for d-axis and q-axis. So here is the rotor lamination and stator lamination, and here is the situation when only we have D current. Yes, so flux lines are in parallel with the edges of the flux barrier layers. And here in this case, only we have Q current. So the flux lines are perpendicular to fluid flux barrier layers in this case, right? We have fluid flux barrier layers. So we will consider this convention for D and Q axis of the rotor core. This is different from the common reference that we are using for IPM motor, for example. Yes, in IPM motor, here, this is the rotor. This is one permanent magnet, another one, and another one. So this is, for example, the direction of the magnetization. And in IPM motor, we consider this as the d-axis and this as the q-axis. Yes, but in this case, we are using this reference frame. The d-axis is when we have the minimum reluctance. Yes, so that is different. I will explain the reason. Formulations will be meaningful if we use this reference. So the d-axis is when the stator field has the minimum reluctance in front of it. And the q-axis is when the stator field experiences the maximum reluctance or maximum magnetomotive force drop. So here we have two figures. We will do the finite element analysis and generate these plots later. And this red vector shows the stator current phasor. This is the d-axis of the rotor, and this is the q-axis, and this is the situation when the current angle is 0 electric degrees and the stator field, right, aligns with the d-axis of the rotor. And in this case, we set the current angle equal to 90 electric degrees, and flux lines are perpendicular to the fluid flux barrier layers, and we have the maximum reluctance path here. So in this figure, also you can see the local saturations that we have at tangential ribs of the rotor core. Yes, in this case, when the current angle is equal to 90 electric degrees, at tangential ribs, we have these local saturations. So this is just an introduction, and later we will do the finite element analysis and regenerate these graphs together. This structure is a synchronous reluctance motor, and we don't have any permanent magnets in the rotor core. But the synchronous reluctance motor has two disadvantages. The power factor is low, and in the case of improper design, when we don't have a good saliency ratio, the value of average torque is low. And to improve the performance characteristics of the motor, we can add permanent magnets to increase the value of power factor and to improve the average torque. So in these structures here, as you can see, we are adding permanent magnets, yes, to improve the performance characteristics of the motor. This image is from this reference, one of our references in this course. So when we add magnets, as you can see here in this graph, some part of the magnet flux saturates the tangential ribs and the rest cross the air gap, right? Some part of the magnet flux saturates the tangential rib and other part cross the air gap to involve in torque generation. So this part that saturates tangential ribs improve the saliency ratio. Yes. So this is important. And here the name is PM assisted. We are not designing an IPM motor. Yes. In IPM motor, the main part of the output torque is alignment torque. So here in this case, the focus is on reluctance torque and add magnets to improve the power factor and average torque. Yes, not designing an IPM motor. This is important. So if we consider strong magnets in this design, so we deteriorate the performance characteristics of the motor. So one topic in design of this motor type is optimal calculation, right, of the magnet flux, optimal sizing of the magnet flux. So here in this graph, you can see the comparison between the synchronous motors versus the torque type. So here, the synchronous reluctance motor, the total output torque is reluctance torque. And in a surface permanent magnet motor, synchronous motor, the total output torque is PM torque. And in IPM motor, the 70% to 80% of the output torque is alignment torque. However, we have reluctance torque. And in PM assisted motor, the main part of the output torque is reluctance torque. And also we have magnet torque. And in the hybrid motor, 50% of the torque is reluctance torque and 50% is PM torque. So now let's review some important characteristic curves of the synchronous reluctance motors and PM assisted motors. Later we will calculate these graphs using the finite element analysis. Here you can see the aligned and unaligned linkage flux curves. So this figure is for the reluctance motor and this is for PM assisted motor. And here we have the flux linkage in the rotor reference frame. The equations, you know that the D flux is LDID and the Q flux is LQIQ minus lambda M. So why negative I will explain later. This is also is our convention here. So this is the geometry of the motor. Yes. the rotor core of a synchronous reluctance motor, and here we have one fluid flux barrier layer and another one here. This is a permanent magnet and a permanent magnet that we have here. So as you know, this is the d-axis of the rotor core in the direction of the minimum reluctance, and this is the q-axis, 90 electric degrees ahead of the d-axis. So here we have these two equations. The lambda d is LD ID, and lambda q is equal to LQ IQ minus lambda m. We will derive these equations later, so this is just an introduction. So this is the direction of the magnet flux, lambda m in this direction, and here is the lambda m in this direction. So the lambda q is LQ IQ minus lambda m, right? The direction of the flux is in opposite direction of the q axis. So when the value of current angle is equal to 0, as you know, only we will have D current. Yes, the Q current is 0. And when we excite the stator winding and set the current angle equal to 0 and increase the excitation level, we can calculate lambda D, right? So this red curve is the aligned flux linkage versus the current level. Lambda D is equal to LD ID. This equation. Yes. So we increase the value of ID and calculate the D flux linkage, this red curve. So as you can see here, this red curve is similar to the HP curve of electric steel. Yes, we have increase in the value of flux, and then we have the saturation region here. So this is the case. We set the current angle equal to 0 and increase the excitation level. So the value of reluctance in front of the stator field is low, and it's limited by the saturation of the iron core. So this graph depends, this red curve depends on the HP curve of electric steel that we use for manufacturing of the rotor and stator core. What about the q-axis? When we set the value of current angle equal to 90 electric degrees, the value of ID is 0 and only we have IQ. In the case of pure synchronous reluctance motor, this is 0. So we can plot lambda Q versus IQ. So this is the case, this blue curve that we have here. So here we have a small saturation and then we have a straight line. So this small saturation is because of these tangential ribs. You know, when we set the value of current angle equal to 90 electric degrees and increase the excitation level, first we saturate the tangential ribs, and then when we increase the current level, we have this straight line because the value of reluctance is high and is determined by the rotor geometry. So the blue curve depends on the rotor geometry, you know, and you remember the area between the aligned curve and unaligned curve determines the value of average torque. Yes, when we have a big area between the aligned and unaligned flux linkage curves, it means the saliency ratio of the rotor is high. Otherwise, the saliency ratio of the rotor is low. So let's summarize. The red curve depends on the HP curve of the material, and the blue curve depends on the rotor geometry. If you have a bad design, so you will get this blue curve and the slope here is high, the saliency ratio is low. And as long as you optimize the rotor geometry, you can reduce the slope of this line, yes, to improve the performance characteristics of the motor. So this blue curve depends on the geometry of the rotor core. And here we have the flux linkage characteristic for the PM assisted motor. The D, lambda D, is almost the same, D flux linkage, and Q flux linkage is shifted by negative of lambda M. Yes, here you can see the blue graph that is shifted in this direction. Here you can see the calculated values using the finite element method. Yes, this is the aligned and unaligned flux linkage curves for synchronous reluctance motor and for the PM assisted motor that we will calculate using the finite element analysis later. So the next important graph is the static torque curve. Yes, the static torque curve is important in synchronous motors, and that is the total developed electric torque versus the current angle. So here in this graph, you can see the static torque curve for the synchronous reluctance motor. And as you know, when the value of current angle is 0, the value of electric torque is 0. And when the value of current angle is equal to 90 electric degrees, the electric torque is 0. These two situations. Yes. You know, the frequency of the reluctance torque is 2 times the frequency of the alignment torque. Yes. So here, when we set the value of current angle equal to 45 electric degrees, when we don't have saturation in the iron pass, we will get the maximum reluctance torque. Yes. So in real case, we have these graphs. And as you know, when the level of excitation is low and we don't have the magnetic saturation in iron pass, the maximum reluctance torque occurs when the current angle is equal to 45 electric degrees. You remember this equation for the reluctance torque? Yes. The reluctance torque is 3 divided by 2, P divided by 2 number of poles, LD minus LQ, ID, and IQ. So we know that ID is IS times cosine of the current angle, and IQ is IS times sine of current angle. So we can write IS to the power 2 divided by 2, and this is sine of 2 times alpha. So when we have the maximum value for this expression, when the value of alpha is equal to pi divided by 2. But this is for the linear case and when we neglect the magnetic saturation. So yes, in this case, the maximum average torque occurs when the current angle is equal to 45. And as you can see here, when we increase the excitation level, the maximum torque occurs at a current angle higher than 45. And this is the graph for the PM assisted motor. For PM assisted motor, in compare with the reluctance motor, the maximum torque is higher. Yes, if you compare this graph and this graph, so you can see the effect of the magnets in the static torque graph. Later, also, we will calculate the static torque graph for the synchronous reluctance motor and for the PM assisted, and we will compare. So this blue graph shows the static torque for the synchronous reluctance motor, and this red graph shows the static torque for the PM assisted. Here, as you can see, when the value of current angle is 0, we have this torque, this amount of torque for PM assisted one. So because this is the case, 3 divided by 2, P divided by 2, lambda M, yes, I, D. This is the case when we have permanent magnets, and when the value of current angle is equal to 0, we have ID, and this is the value of torque that we have here for the PM assisted motor. Anyway, later we will discuss and calculate these graphs in the software. Here you can see the vector diagram of the synchronous reluctance motor and PM assisted motor. The vector diagram is important. That is used for optimal sizing of the magnets that we will discuss later. So let's review here. This is the D-axis of the rotor core, and this is the Q-axis of the rotor core. This is the IS, the stator current phasor. Yes. So when the stator current phasor, the angle alpha IE, this is the angle of the stator current phasor. When this angle is 0, we have this case, and when the angle is equal to 90 electric degrees, we have this case. So here I set, for example, alpha IE equal to 60 electric degrees to get the maximum electric torque. So this is ID. Yes, if we decompose this vector on D-axis and Q-axis, this is ID and this is IQ. So this is LDID and this is JLQIQ. Yes, so this is the stator flux linkage phasor lambda. Yes, in the case of a synchronous reluctance motor, this is LD, ID, lambda D, and lambda Q is LQ, IQ. So this. And you know that the stator voltage phasor is 90 degrees ahead of the flux linkage phasor. If you neglect the resistive drop, this voltage phasor that we have here, and you can see the Q component of the voltage phasor and the D component. So this angle is the angle between the voltage phasor and current phasor, phi. And as you can see here, this angle is high, and this is why the value of power factor is low in this motor type. If you want to reduce the value of phi, you should increase the saliency ratio. Yes, you should increase LD and reduce LQ. Yes, to reduce the angle of the flux linkage phasor, to reduce the value of phi and increase the power factor. But we have an analytical derivation in this reference. You can refer to this reference and read the procedure, neglecting the magnetic saturations and so on, and calculate the value of power factor versus the saliency ratio. So as you can see, when the value of saliency ratio is high, for example 5, 6 or 7, still the value of power factor is low. So the blue graph is when we drive the motor considering the maximum power factor condition, and this red curve is when we drive the motor considering the maximum torque per ampere. Yes, so as you can see here, even for high value of saliency ratios, the value of power factor is low. And how we can reduce the phi angle? So here, if we add magnets lambda m, this flux, in opposite direction of the q axis, yes, so the value of flux linkage phasor is equal to, here you can see the equations, LQIQ minus lambda m for lambda q, and for lambda d, LDID. So this is the case. Yes, LDID, this is JLQIQ, negative of J lambda m. So the voltage phasor is 90 degrees ahead of the flux linkage phasor and is here. So we have a good reduction in the value of phi. So as you can see here, when we add magnets, we can improve the value of power factor. But how much depends on targets. For example, you want to design a PM assisted motor considering power factor equal to 0.8, 0.9, or even 1. Yes. So first you design a pure synchronous reluctance motor and optimize it. Then you can consider magnets, yes, and calculate the value of phi and increase the value of the flux linkage due to magnets step by step, and check the performance characteristics of the motor. So the vector diagram is really good, and we can realize why the value of power factor is low in this motor type. So this graph shows the torque map for the synchronous reluctance motor. Here we have the D-axis current and Q-axis current. The first quadrant is important in this motor type, so we should change the value of ID and IQ in the first quadrant and calculate the electric torque to plot the contour lines and calculate the torque map. Yes, so we will calculate the torque map for the design later using finite element analysis, and after calculation of the torque map, we can calculate the efficiency map and so on. So here also you can see the difference between the torque map of a synchronous reluctance motor and a PM assisted motor that we will calculate later in software. And here you can see the maximum torque per ampere for this motor type. As you can see, when the excitation level is low, this angle is 45, and as long as we increase the excitation level, this trajectory tends to approach the q-axis. Yes, MTPA, maximum torque per ampere trajectory, is something like this. So the aim of this introduction section is to review the performance characteristics of the motor vector diagram, and then when we calculate these quantities using the finite element software, we can judge the results, right? So anyway, in the next video, we will start the design of the stator core in the software. Yes. And after that, we'll focus on the rotor design. Thanks for watching.